So, uh, today I want to talk about specifically about issues that come up with different metrics on the same space. On the same space, and I want to talk about what does it mean to converge with one metric and how you can make sense of it in terms of other things um, in the space. So, practical things where you see different metrics is, for example, in image processing. You want to identify how similar two pictures are. So you have this beautiful picture of a cat that yours truly drew, and then you have this picture of a very obese cat gotten from online, and you want to understand how similar these pictures are. And You could do different things, and depending on your application, depending on what you're doing, and this is an open question of research, what is the best metric? One option would be you look at the values or say the RGB value of each pixel. I mean, this is a very crude thing. This would not work in practice very well. And you look at how different those values are. You sum up those differences in the L1 metric, or so-called taxi cab metric, and then you call this the distance. Well, this certainly does satisfy the triangle inequality, positivity, zero, symmetry. It might not be exactly what you want to do in practice, but it's something to start from. But there are many other metrics that are not so sensitive to exactly these pixels being used. For example, some metric might notice that this picture is sort of a reflected version or different orientation of that. And the pixel-wise RGB values would not detect that. So you would want to look at other things, and one option is to look at some so-called feature vectors and then looking at some distance between them. And that can be understood a little bit better with thinking about documents. You could think about articles, about one group being articles related to Corona and another being articles related to international politics. And how, say, would you automate grouping these into specific groups? Well, you need some notion of a distance between different articles. And you don't want to do a word by word comparison of just letters and seeing how many are same and how many are different. That doesn't really tell you much. But what you can do is you can extract features. And for documents, those features are quite intuitive. Namely, they are word counts. You take the most important words, you maybe exclude, prune out some words like A, B, etc. And you create a feature vector that's in some high dimensional RD, and that indicates how often, say, certain words are being used. And then you can define a distance, so-called angular distance between these vectors by taking the angle between them. And that can be computed by the cosine between these, cosine of the dot product divided by the norms. Now, there are many, so one can verify certainly that this angle between vectors satisfies the triangle inequality. It's certainly is non-negative by the choice of the angle. We choose the angle between 0 and pi. And it has a symmetry property. The angle between V and W is the same as the angle between W and V. But a remark of a little bit of interest is, though, that it's not very convenient to compute. It's kind of annoying doing this cosine inverse. And for applications, that doesn't really matter. So sometimes people use a different measure, 1 minus the dot product divided by the norm. This is kind of a cruder measure of distance, and it's sometimes called the cosine distance between these pairs of points in documents. And it doesn't quite satisfy the axioms of being a metric, but mainly it does not satisfy the triangle inequality. But why I mention this is I want to get you thinking about what is an appropriate metric in a different context, say in the context of documents or the context of images. And that's one of the big reasons why we are introducing and spending so much time on thinking about what is a metric and what different kinds of metrics we would look at. Now, Often these norms or the similarity metrics between different things, well, you extract some features and then you look at how similar these features are. One option is to look at the angle between them. It has some shortcomings. For example, the same document of different length or a very similar document of different length, they will point the same direction and therefore their angular distance would be 0. So it fails actually one of our axioms that distinct documents have to have non-zero distance. So it's not maybe ideal in every way. So there are different measures you could use, and one of these is these LP distances that we are using. So, and a specific one of these is the so-called infinity distance between two sequences. So distance between AN and A, this is a sequence of real numbers. We list these elements this way. And then we define the distance between them as essentially the largest distance between each of these components, ANI minus AI. So this is the distance. This makes sense, not quite for every sequence, but only for sequences that themselves are bounded. So we are looking at sequences A1, A2, A3, ... such that supremum over I of AI is less than infinity. This space is sometimes called the L infinity space. But now, relating to this metric, or just thinking about these sequences, there are two notions of convergence. One is that comes from our metric that we have now defined. So we say that AN converges to A if limit as n goes to infinity of the distance, infinity distance between AN and A is equal to 0. So I'll get to that question in a second. So this is one of the convergence ideas of convergence. But then there is a completely different, at first it seems like a different notion of convergence, that is that we look at every one of the components individually. Now, maybe it's useful to draw this as a picture. So we have, and maybe this answers this question a little bit. We have our first sequence. Well, this is a sequence of real numbers. So A11, A12, A13, ... And then we have our second one, A21, A22, A23. And this is a little abstract because we have a sequence of sequences, but the way to imagine is that we have this huge table of values, and our objects are the rows of that table, the rows of this sort of huge matrix. And we're looking at what happens as we go down along the rows of this. So we have AN is AN1, AN2, AN3, ... And we're hoping for this to converge to something, A1, A2, A3, ... Here I drop the subsequence or the subscript, because the subscript here in this notation is indicating which element in the sequence I am using. So the element, whether you use a subscript or superscript does not matter for this, but you have to be consistent. So the subscript 2 means that you're taking the elements from the second sequence. The subscript 1 means that you're taking the elements from the first sequence. So you have to be consistent on which one you choose. And that can create a little bit of a mess, but it's something. So one is that we just look at the distances of these full sequences to A, and we insist that they converge to 0. This is what we defined last week as convergence. But there's another sense in which we could talk about convergence. Namely, we could look at these real numbers, A11, A21, A31, up to AN1, and so on and so forth. And we could look at, do these converge, so-called component-wise, to the limit? So we could ask, is it true that for every I in natural numbers, that limit of x, a and I is equal to an? So here we are taking the ith component of the element an, the infinite sequence an, and we're asking whether that converges to the one in the limit an. Does that answer your question, Max? So it doesn't matter which you use, but you have to be clear which index is matching the components, which one is matching the sequence. It takes some time to get used to this, for sure. So to get used to it, the best thing to do is to work with examples. So and to show that these are different. In full generality of infinite sequences, these give you a different notion. We'll see one place where they're actually the same. So these two notions, one, so-called component-wise convergence, and two, so-called uniform convergence. And these two differences, these will come up again when we talk about functions and functions converging. So that it's good to start to getting an intuition about these at the level of sequences and sequences of sequences converging. So let's call an to be the sequence that is all zeros up to the nth index, and then it's more zeros. So you could define a and I to be equal to 1 if I is equal to n. So this is sort of like a Dirac notation for those who know that. And for all the other indices, this sequence is giving 0. So what does this look like? It's a good way to draw these is we have our, I mean, this is only a value. We have sequences, so that could be thought of some sort of a function on n, and an, the graph of an would look like it's all zeros up to the nth index when it's 1, and then after that it's again all zeros. So it's some sort of a bump here at the nth index. And what is happening as n goes off to infinity is that this bump is moving to the right. It's moving to the right until it passes off to infinity. So as n increases, the bump is moving to the right. So we could ask, in what sense does the sequence converge? Well, if we look at the infinity metric, then, well, actually, yeah, sorry, let's not look at the infinity metric first. Let's first look at component-wise. So this is our first notion of convergence that up above. So component-wise. Well, so component-wise, we're fixing an I. We're looking at limit as n goes to infinity of a and I. Well, this sequence, a and I, is eventually 0. It's a constant sequence when you hold I fixed. So this is a and I is equal to 0 if n is greater than or equal to, or strictly greater, well, greater than or equal to I plus 1. Because after that, it's always equal to 0. It's never equal to I anymore. So this is just limit of 0. So each of the components is going to 0, and that corresponds to the fact that you're taking this peak and it is escaping off to infinity. However, if we use our notion from earlier, let's look at the distance infinity between an, the sequence an, and the sequence of all zeros. Well, this distance is supremum over I of a and I, I natural number, now minus 0. And well, we have minus 0, that doesn't matter. A and I are all positive, so this is the supremum over I natural numbers of A and I. Absolute value goes away because it's positive. This is either 1 or 0, so the supremum is 1. So it's not converging to 0. And therefore, the sequence AN does not converge to the 0 sequence in the L infinity metric, in D infinity. So what this is, the main point of this is that the notion of distance and the notion of convergence can heavily depend on what you're actually using. So to give an example of something where it is actually converging in the L infinity metric is, let's look at the sequence AN, that is 1 over n squared, 1 over n cubed, etc. So the formula would be a and I, the ith component of the sequence AN, would be 1 over n to the I. And these elements are all converging to 0 component-wise. So fixing an I, we get that limit n goes to infinity a and I, which is limit as n goes to infinity 1 over n to the I is equal to 0 by the, say, p convergence, some sort of p test. But also, if we look at the distance of the sequence AN to 0, so this gives us component-wise convergence. And we get 1. But if we look at the second possibility, distance infinity, AN to 0, and let's put the limit here because we will be computing the limit as being equal to 0. So the limit as of D infinity AN, well, this should be the limit, assuming that it exists, of the distance is the largest difference in the components. So supremum over I, A and I minus 0. And this is limit n goes to infinity. Now this supremum you can evaluate as the largest component, which is 1 over n. And this limit is equal to 0. So limit n goes to infinity of an is equal to a, is equal to 0, which is, we call a in the D infinity metric. So there's a good question. So the subscript of a to the I, this is an I converging. And here the sequence is 1 over n squared, 1 over n cubed, etc. A and I, the subscript is just n. So like this. So a n I minus 0. Thank you. That was a good question. So by playing with these examples, and also you'll see this, there's a number of questions in the chat rooms on Campus Wire and in the newsfeed, there's some good discussion on this point. Convergence and what it means by convergence depends on the context and depends on the metric you're using. So convergence depends on the metric. And sometimes it can be a little different from what, there are different senses of convergence. Meanings for convergence. So when can you use that the distance is equal to the supremum? You have to look at the problem that you have given to you. So here, we started the study by looking at this infinity metric. There are other metrics that you could use. And there will be a whole video uploaded later tonight or tomorrow about different metrics. So one could add a remark that there are other notions of convergence. That correspond to different metrics. So let's just say other metrics. For example, D1 between AN and A could be the sum of the differences in the components, absolute value. So then you cannot use. Sorry, component, thank you. This is a typo. I meant to say n goes to infinity. So the sequence n is going off to infinity, and we're looking at a fixed component. So we're going down along a column like this. We're saying that these elements converge for fixed I as n goes off to infinity. So correct, yes. This would be n goes off to infinity. Okay, so lessons, indeed, we have different notions of convergence for the same space. And in the case of infinite dimensions, indeed, one has to be very careful about what metric you use and what notion of convergence you use. Because as we saw here, the notion that we defined last week in terms of the distance, in this case, the infinity distance, is different than if we define component-wise convergence. So fixing I and sending an n to infinity. And it's even different than if we define other metrics on the space. So this is kind of an annoying setting. You have to be very careful about what notion of convergence you mean, and depending on what you're doing. So indeed, good news is that in finite dimensions, we can be a lot sloppier. So there, we don't have to worry as much about convergence, and that's the good news about this theorem. So on RD, we can still define many different metrics. We can define for every p between 1 and infinity, we can define the dp metric between two vectors, x and y, and I'll denote the components by superscripts. And the distance between them could be defined as x I minus y I to the power p 1 over p. And this you can define for any p between 1 and infinity. The proof that this is satisfies the triangle inequality is a little tedious. This was done in this inequality 2 video, but it's a little bit supplementary material. The p equals 2 case involves Cauchy-Schwarz, as discussed in these supplementary videos. And then there is an additional metric corresponding to infinity, given by the distance of two vectors, x and y, and these are x and y are in RD, is given by the supremum over all the components. So this is I in 1 through n of xi minus yi. And you'll notice that this is very different, similar to the metrics that we actually defined on L infinity, this infinite sequence space, except that now we have finitely many components. And the good news is that in finite dimensions, so if we have Pn converging to Pn, then the following two things are equivalent. So if Pn is a sequence in Rd, then the following are equivalent. So 1, for every I equals 1 through d, we have limit and then goes to infinity p x and I is equal to xi, and this x are components of a vector in Rd, xi. So this is the component-wise convergence. And 2 is the convergence in metric. That is dp of pn and p, limit n goes to infinity, is equal to 0. So the second was what we said, that limit of pn is equal to p in the metric dp. The following are an equivalent. It's a convenient TFAE is a convenient equivalent abbreviation for the statement. It's just that the following are equivalent. So you could add in this middle equivalent statement. You'll find this in many places, many books, many videos online also use this convention. Now, okay, so in finite dimensions, these are the same notion. And this matches what you've learned in multivariable calculus. 32a usually starts with defining the limit in terms of 1. So this really proves that actually both of these are the same notion. There's no contradiction in using one or the other. It also has the corollary that the convergence doesn't depend on p, which is nice, because then we don't have to be so careful about which metric we are using on Rd, because there's really only one notion of convergence on higher dimensional Rd. In infinite dimensions, it's extremely important, but in finite dimensions, you can be a little sloppier. So we want to prove one implies the other and vice versa. So in both directions, there is a crucial estimate that plays a role. So we're going from 1 to the 2. We know that each of the components are converging. So each of the components are getting very close. And then we want to say something about the distance. And I should say, I'll only prove this, give a proof for p between 1 and infinity, not including infinity. The infinity case is an easy exercise based on what you see here. This is a good problem to think about. But for p equals infinity, what I would like to say is that if I know that the components are close, I would like to say that the distance is small, because I want to say something about distance converging to 0. So the crucial estimate is, it's true for any two sequences, the two vectors, let's call them x and y. Distance p between x and y is at most n to the power d to the power 1 over p times the maximum over I equals 1 to the d of the difference in components. So this is the crucial estimate. Let's prove this estimate. Distance p is, so the left-hand side is equal to n equals 1 to d xn minus yn to the power p, absolute value to the power p, 1 over p. Well, each of these components is less than its maximum, so this is less than n sum over the maximum, I equals 1 through d of xi minus yi, and this maximum to the power p, and 1 over p. Now this is a constant, so this expression inside, it's just d times the maximum, xi minus yi to the power d, p, and then the power 1 over p, and this is the conclusion of that. Any questions on this estimate? Okay, so how do we use this estimate? Well, the idea is that because we know component-wise convergence, we can make every one of these individually small. So let's do that. So we know that for I equals 1 through n, 1 through d, we have limit x and I equals xi. So for every epsilon, there exists some capital N, I, such that, and I'll imagine that I want to cancel out that factor d in this definition. So such that xni minus xi is less than or equal to epsilon over d to the power 1 over p for all n bigger than or equal to ni. So for each of, we have d sequences. For all of them, 1 through d, we apply this statement, we get a different ni. And this is where finite is different from infinite dimensions, is now we can, because we have finitely many, we define n as being the maximum of ni, I equals 1 through d. If n is greater than or equal to capital N, then distance between Pn and P, well, it's less than d to the power 1 over P times maximum, I equals 1 through d, of x and I minus xi. But because n is bigger than or equal to n, which is bigger than or equal to ni for all I, then each of these components we can estimate from above by epsilon over square d to the power 1 over p. This is a maximum, so it's at most, and we have the same upper bound for all of them, so we get d 1 over p times epsilon over d to the 1 over p. Factors cancel, we get epsilon. So for all n bigger than or equal to n, we get distance Pn, P is less than or equal to epsilon. And this is the same thing as saying that limit as n goes to infinity, Pn, distance Pn to P using the P metric is equal to 0, or the same thing as saying that Pn converges to P. Any questions here? So we started from the assumption, we applied it in the beginning. We did this for every epsilon, and for every epsilon we found an n such that this is less than that. So by the definition of convergence of real numbers, we're good. Okay, other direction, and this one I'll do a little hastier because we don't have so much time. So going the other way, we want to start from the distance going to 0, and we want to say something about the components. Well, this time we want to say that maximum is 1 through d of x and I minus xi is at most the distance p between p. We want x and y here. Xi minus yi is at most the distance between x and y. And this is an easy exercise because if you have the sum of terms, you estimate you drop all the remaining terms and you're left with this estimate. Okay, so this proof I skipped, proof exercise. Okay, but what does this give us? Well, since limit n goes to infinity, Pn is equal to P, we know that for every epsilon positive, there exists an n such that distance P of Pn and the limit value P is less than or equal to epsilon for all n greater than or equal to n. But then we know that x and I estimate, x and I minus xi is less than or equal to epsilon for all n bigger than or equal to n. So actually the same n works for all I. And there's a bit of a glitch on my end. I'll restart the, sorry about that. Well, that's the new normal, I guess. And it doesn't scroll. Well, at least you see the end of the proof that I wrote, that x and I minus xi is less than or equal to epsilon for every n bigger than or equal to n. And it's a little bit okay, sort of responsive. Okay, so that gives us the other direction. So in the Rn case, both of these convergences give the same meaning. Now, I want to end with another context. This will just be some light examples. We'll continue on this on Wednesday. And feel free to ask me if anything was left confused about that proof. But so even in R, the idea, and especially for subsets of R, you can still come up with contexts where the notion of convergence really depends on the metric. So, okay, in Rn, it's all just the same as component-wise convergence. But let's look at different metrics that you could put on R, where you get a different thing than what you would normally expect. So let's look at R equipped with the discrete metric. You saw in their discussion and in the notes for that discussion that this is indeed a metric. And the question I would like you to ask you is that if I take the sequence xn equals 1 over n, then does this converge? I mean, we guess that it converges to 0. So feel free to answer in the chat. What do you think? Does it converge to 0 or does it not? No, yeah. So why would it not converge? Well, because if we look at the distance xn to 0, say, then the distance from xn to 0, well, 1 over n is not equal to 0, so it's equal to 1. It's not converging to 0. You could ask, does it converge to anything else? Well, for the same reason, again, it cannot converge. Actually, you can show, and this is a good exercise also, that xn converges in the discrete metric only if there exists some capital N such that for all n bigger than or equal to n and m bigger than or equal to n, xn minus xm is equal to, or xn is equal to xm. Exactly. If it's eventually constant, and in this case, it's not. So we get a very different notion of convergence if we play with this discrete metric. Now, another a little bit milder case where the metric makes a difference is if we look at the open interval, 0 infinity. This is our space X. And we look at the distance. It is not the usual distance x to y, but is the difference of the absolute 1 over x minus 1 over y. Now, you can verify the axioms of metric space here. There's actually an example on CampusWire. If you go to the discussion about metric spaces, there's a great example on this that gets exactly, that basically proves this, that 1 over x, this is a metric. But we could again ask, does xn equals 1 over n converge? At least, well, specifically, does it converge to 0? Because that is what our instinct would say, that, well, yes, it's converging to 0, but no, and there are two reasons. Well, first of all, it cannot converge to something that's outside your domain. 0 is not in your space. you can't converge to something that's not in your space. That's one of the basic considerations that you have to factor in. This is something that comes up in relative topology, but there's a bigger issue why you don't converge to zero. Well, if I look at, and this is something we will discuss much more on Wednesday, if I look at distance between xn and xm, and I look at, so this is 1 over n minus 1 over m. This is the same thing as n minus m. Well, so this means that this distance is always bigger than or equal to 1 if n is not equal to m. And now, if you are converging to something, your points should be getting closer to something. And if they get closer to something, they get close to each other. So we should have a Cauchy sequence. And we'll define this on Wednesday. But not Cauchy. Because the distance, essentially, for it, as long as we take different n and m, the distance is 1. In fact, the distance restricted to this set is a discrete metric. So this is a very much non-convergent object. Okay. And another way, exactly how this context matters, and this is something I want to make clear, is that if you take the same set, then depending on what you're in, you can either be open or closed, and that depends completely on the context you're in. For example, the open interval, the half open interval, 0, 1, well, it's neither open or closed in R, but you can find a domain where it's closed. So if you take the interval -1 to 1, then A is open, is closed in X. And conversely, if you cut this out a little bit differently, say you take the same set, then A is open in X. So it really depends on the context. And where the issue comes from is that all of these notions are always defined relative to X. So say, I mean, your instinct might be that, oh, it can't be closed because you have this limit point 1 that's not inside the interval. Well, if you look at the definition of closed, for every sequence of points in A and for every x in X, if limit as n goes to infinity of xn is equal to X, then X also belongs to A. But 1 does not belong into X, so we don't get a contradiction. So the only point, sort of the only missing limit point is 1, but that lies outside the space, so the set is still closed. Looking at this other case, your instinct might be that, okay, well, the ball at zero prevents this from being open. Well, that's in R, but if we're looking at the ball centered at 0 of, say, radius R in X, then we're only looking at values in the interval 0, 1. So we're looking at Y in the interval 0, 1, such that distance Y to X to 0 is at most R. But we're only interested in those that are in the space X, and therefore, actually, this is a subset of R, A, because A is equal to X by the definition. Okay, so context matters in many ways. It matters which metric you use. It matters what is the set you're considering of possibilities. So both the set and the metric matter. Fortunately, sometimes we can get equivalences. So in Rn, it doesn't matter what metric you use, and you get that. So to summarize the statement that we proved in some of these discussions, if we have two metrics, P1 and P2, and if Fxn converges, and we have a sequence and a possible limit point, then if that sequence converges in the first metric to X, then it also converges in the second metric to X, and vice versa. So this is an if and only if statement. And the proof is basically we apply the theorem. So by theorem, the statement that our Xn converges to X in dp1 is equivalent to Xn converges to X component-wise, but then applied in reverse, Xn converging to X component-wise is the same thing as limit Xn is equal to X in dp2. And that concludes that proof. So really, in Rn, the notion of metric, even though you generally have to be careful about this, it doesn't make a difference for their convergence. So that ends the lecture for today, but I'll stick around definitely for a few more minutes to answer questions that you may have on the topics. So feel free to post questions in the chat. Also, you can unmute yourself to ask questions. So corollary, if you have a sequence of points, then it converges in dp1, if and only if it converges in dp2. Other questions? So on Wednesday, what we will do is we'll discuss a little bit briefly some issues about convergence a little bit more, and we'll define Cauchy sequences, and we'll talk about what it means for a metric space to be complete. And yeah, so about the enrollment, yeah, the situation is right now, I'll send a post about this on CampusWire, that there is no budgetary possibilities to hire a grader. But given the large interest in the classes, both sections, Professor Brown's and my section, will be raised, and enrollment will be raised to 50. And that means that 10 additional people will be able to officially enroll. There may be a few drops, of course, given the circumstances. That might be a little less than usual. Unfortunately, it does likely mean that there is about probably 20 or even 30 or so people who don't, despite their interest, don't get to enroll. I find this unfortunate, but we don't have the resources right now to increase the enrollment past those amounts. So. Sure. So proof here is that, well, both of these statements are equivalent to component-wise convergence. Now, if you have one thing equivalent to something else and another thing that's also equivalent to that, then they're equivalent to each other. Other questions? So yeah, relating to the enrollment, you have to think a little bit. Yeah, for some people, if you went on the wait list very quickly, very late, you might consider that whether you want to do the homework or not, because if you're not able to enroll, it's like, I understand that it's a waste of your time to do the homework. But that being said, of course, everybody who, if there's any confusion about this, I'm happy to, of course, grant extensions for those who are if somebody got enrolled and decided for some reason that they did not want to do the homework and then later realized that they could get enrolled after all. So, but I would recommend to think about that. Any other questions? I'm sure the sequence space stuff at the beginning might have been a little bit confusing. At least it's usually quite confusing the first time you see it. So there's another video that will talk about the function spaces and the sequence stuff. That's completely supplementary, but I think to understand these things well, you might very much enjoy watching it. That's a yeah, great question. So indeed, the discrete topology and the discrete metric define the same thing. So for those students who are taking both classes, maybe I can have just a few seconds on this. So a topology is just declare the open subsets of X. You give some rule for specifying open subsets. Now, and that they have to satisfy certain axioms, namely the finite intersections should be there. So X and the empty set have to be in tau. 2, if I take any unions of collection of sets in tau, they have to be in tau. And 3 is that if I take finite intersections, they also have to remain in tau. But these are axioms of a topology. And how metric spaces relate to that. So if XD is a metric space, then we can define tau as the collection of O such that for every X in O, there exists a radius positive such that the ball at X of radius R is contained in O. I mean, this means open in D. So now let's compare. So there's X, the discrete topology can be defined. Can be defined as you take tau equals all the subsets of X. I mean, this always satisfies these properties. Well, empty set and full set are sets. A union of sets is a set. Intersection of a set, even arbitrary intersection, you don't even have to worry about the finite. So this is always a topology. But we also have the discrete metric that gives you 0 when X is equal to Y, as not equal to Y, as equal to Y. Getting a little tired, I guess, with it being 11 p.m. and X not equal to Y in that case. In this case, there's a note on campus wire that basically says that omega O subset of X, every subset is open. And the reason is that, well, if I take the ball at radius a half, well, I don't include any other points because the distance, everything else is half. So this is always equal to just X in this metric. So for every X in O, if you take R equals 1/2, then BX R is contained in O. So O is open. So every subset is open, and these topologies are the same. So yes, I'll take one more quick question if somebody has, but otherwise I think I'll need to go to sleep. I'm happy to discuss these, by the way, at anything else in the discussion in the office hours or also at the right before the Wednesday lecture. So do collect questions, and if you don't get a question now answered, ask it online, and I'll look at it, and maybe somebody else might answer it as well. So xn equals 1 over n does not converge in the discrete metric in R. Now, this is just convergence in R, so there is no component-wise convergence. Component-wise convergence is an issue of RD because we have many components, x1, x2, xn. So when you have a sequence of points, you can look at each of the components individually converging. But if you are in R, you just have a single real number. And this time we don't have this ambiguity. There is no notion of component-wise convergence because there is only one real number converging. But so you can vary, but you can still vary the metric. So in that case, there's the issue of component-wise convergence is really about Rn, higher dimensional space, or infinite dimensional space. But thank you for these questions. If you have any other questions, just post them on Campus Wire. But have a nice rest of the day. Bye for now.